My dear students, welcome to Department of Chemistry, Sri JCBM College Sringeri. I am Devdas K. In my last video class, we have seen the paraker, use of paraker in the structural elucidation of the molecules, and molar refraction, and the use of molar refraction in the structural elucidation. So we can recap the things that we have seen in the last video class. So what is meant by paraker? The paraker may be defined as the molar volume of a liquid at a temperature so that its surface tension is 1 or unity. So then we have seen the use of paraker in elucidating the structure. The paraker is both an additive and constitutive property. The paraker of an individual compound can be expressed as the sum of atomic parakers and the structural parakers. By correlating the experimental values of paraker with molecular structure of the molecule can be elucidated. So last time we have seen the structure of benzene, Kekulé structure of benzene. They accepted the structure is the Kekulé formula for benzene. The experimental value of the paraker of benzene is 206.2. Calculated value of paraker is 206.9. So which is in good agreement with the experimental value. So therefore the Kekulé structure for benzene which is accepted and also they supported. So next we have seen the structure of quinine also. The two possible structures formula proposed for quinine. In that the structure A and structure B that we have seen, the structure A is accepted formula for quinine. So next we have seen the molar refraction. Molar refraction is an additive and constitutive property. The molar refraction of a molecule is a sum of the contribution of the atoms. So that is known as the atomic refractions, and the bond that is bond refractions the present. So then from the observed values of the molar refraction of appropriate known compounds, the atomic refractions of different elements and bonds have been calculated. So that also we have seen. Then the we have seen the structural elucidation of the acetic acid. The you know that the acetic acid, accepted structural formula of acetic acid we have seen, CH3COOH. So in that case the value of molar refraction of acetic acid is found by the determination of its refractive index that we have seen 13.3 cm cube mole inverse. There is a this value is in good agreement between the calculated and experimental value. So therefore it confirms the accepted formula of acetic acid. So then we have seen the Kekulé structure of benzene also. Here the observed values of the molar refraction for benzene is 25.93 and the calculated this one is 26.289. So this is in good agreement with the calculated value, hence the Kekulé formula for benzene which is supported. In my today's class we are going to study, or we are going to deal with the magnetic properties of molecules. Magnetic properties of molecules are useful in elucidating the molecular structure. So first of all we'll see what is meant by magnetic permeability. The force acting between two magnetic poles of strength m1 and m2 lying at a distance r is given by Coulomb's law. F is equal to m1 into m2 divided by mu r square, where mu is a constant characteristics of the medium and is called the magnetic permeability of the medium. Magnetic permeability describes the ability of a material to support the formation of the magnetic field inside itself. The magnetic permeability is defined as the relative tendency of magnetic lines of force to pass through the medium as compared that in the vacuum, for which mu equal to 1. So then depending upon the value of magnetic permeability, the substances are classified into following types. One is the diamagnetic substances. A substance constituting the medium with mu less than 1, mu equal to magnetic permeability is less than 1 is called diamagnetic substance. In these substances, atoms or molecules have all their electrons are paired. Diamagnetic substances are repelled by magnets, and when they placed in a magnetic field, they move from stronger to weaker part of the field. The magnetic line of force deflects away from a diamagnetic substance. Example for diamagnetic substances are bismuth, antimony, copper, etc. Then paramagnetic substances. These substances have one or more unpaired electrons and they are attracted by magnets. For paramagnetic substances, mu is greater than 1, that is magnetic permeability is greater than 1. A paramagnetic substance is more permeable to the magnetic line of force than the vacuum. The magnetic lines of force deflect towards the magnetic substances, and when placed in a magnetic field, they move from weaker to stronger part of the field. Example for these paramagnetic substances are aluminium, manganese, oxygen, platinum, etc. So then ferromagnetic substance. For these substances, the magnetic permeability mu is much higher than 1. These substances are attracted by magnets and can also be magnetized. The ferromagnetic substances show all the properties of paramagnetic substances to a much greater extent. Example for these ferromagnetic substances are iron, nickel, cobalt, etc. Then another concept is magnetic susceptibility. What is meant by magnetic susceptibility? Susceptibility is a measure of the extent to which a substance becomes magnetized when it is placed in an external magnetic field. When matter interacts with the magnetic field, an internal magnetization or polarization, which is designated by J, is created that either opposes or increases the external magnetic field. So magnetic susceptibility is denoted by the Greek letter chi, is defined as the magnitude of the internal polarization J divided by the strength of the external field B0. So therefore chi equal to J divided by B0, where J equal to the polarization or internal magnetization or polarization, whereas the B0 equal to external field, the strength of the external field. Then since it is the ratio of two magnetic field, susceptibility is a dimensionless number. Diamagnetic substances have negative susceptibility, chi equal to less than 0. This means the diamagnetic materials tend to get repelled by magnetic field. Paramagnetic, super paramagnetic and ferromagnetic substances have positive susceptibility. So that is chi is equal to greater than 0. You can see in this figure, if the polarization opposes the applied field, the effective field within the object is reduced. the lines are dispersed and the effect is known as diamagnetism. So you can see in this figure diamagnetic. So that is the polarization opposes the applied field. The effective field within the object is reduced. The lines are dispersed and the effect is known as diamagnetism. Whereas para and ferromagnetic, if the polarization is in the same direction, polarization is in the same direction as the external field, which is represented here J, external field, the magnetic lines are concentrated within the object. So that means the magnetic lines are attracted towards the object, resulting in paramagnetism or super paramagnetism or ferromagnetism, depending on the degree of increase. Then the importance or applications of this one, the magnetic susceptibility. Some important applications of magnetic susceptibility measurements are in the calculation of the number of unpaired electrons in a molecule or ion. Knowing the molar magnetic susceptibility Xm, which can be easily determined experimentally, the number of unpaired electrons present in a molecule or an ion can be calculated. So this has helped in understanding the electronic structures of a number of molecules. For example, the molar magnetic susceptibility of oxygen molecule is found to be 3400 into 10 to the power of minus 6, which shows that it must contain 2 unpaired electrons. Thus, the structure of oxygen molecule should be represented as like this. So, therefore, it is a paramagnetic molecule. Then, in the study of coordination compounds, an important application of magnetic susceptibility in chemistry has been in the study of coordination compounds of transition elements. Measurement of magnetic susceptibility helps us to know the number of unpaired electrons present in the complex, and which in turn helps us to assign the correct structure to the complex ion in some cases. For example, the magnetic susceptibility values of the complexes ferrocyanide, so FeCN6 3- and FeF6 3-, though each has the same coordination number 6, suggests that there is one unpaired electron present in the former case, that is the ferrocyanide ion FeCN6 3-, whereas there are 5 unpaired electrons in FeF6 3-. These are explained by suggesting that means the study of coordination compounds can be studied by knowing the magnetic susceptibility. So next, another application is in confirming the structure of given molecule. The use of molar magnetic susceptibilities in confirming the structure of a given molecule is based upon the fact that the magnetic susceptibility is an additive as well as constitutive property. Then another application of magnetic susceptibility is in explaining the existence of odd electron molecules. The compounds containing odd electrons are expected to be paramagnetic. This is actually found to be so for a few gaseous compounds. For example, nitric oxide, nitrogen dioxide and chlorine dioxide, etc. Their magnetic susceptibility shows that they contain one unpaired electron in each case. So these are all the applications or importance of these magnetic susceptibility measurements. So I will stop at this stage. We'll meet in the next video class. Till then, stay home, stay safe. Thank you.